Welcome to the massive construction site of one of the largest energy machines on the planet. Right in the heart of India's Thar Desert, surface temperatures can heat up to 50 degrees Celsius. Thousands of moving sand and dust blocks rub together every day here, powerful enough to scratch surfaces and destroy the efficiency of any optical equipment. Yet engineers decided to set up a matrix of over 10 million fragile solar panels right in the core of this extreme weather zone. Stretching over an area of 5,700 hectares, the Bhadla Solar Park is producing 2,245 megawatts of electricity. The toughest physical puzzle is, how can engineers operate the giant substation and clean millions of square meters of sand-covered glass every day when this entire area does not have a single drop of industrial water? Let's dissect the entire cooling mechanism and dry robot system of this mega project right now. And don't forget to click the subscribe button and the notification bell icon so you don't miss our latest technical infrastructure analyses. Now, let's get started. To understand why engineers decided to deploy a billion-dollar mega project in the middle of this harsh desert, we need to look at the macro infrastructure picture. India is currently the third largest energy consumer in the world. To quench this thirst for energy and reduce reliance on coal-fired power plants, the Indian government needed a massive space to realize its solar ambitions. To optimize power generation, the first puzzle was finding a location with maximum solar radiation levels, and the Bhadla region, deep in the Thar Desert of Rajasthan state, perfectly met this standard. With over 300 days of harsh sunlight each year and completely clear skies, this barren desert, completely unsuitable for agriculture, instantly became a strategic location for harvesting solar energy. However, as soon as construction began, engineers immediately faced a severe mechanical risk regarding the foundation. The surface sand layer is dry and loose, with absolutely no cohesion. It cannot support the static load of the massive steel frame system. Pouring traditional reinforced concrete foundations for this entire area was impossible due to material transport and time constraints. To solve this geological puzzle, engineers used the method of hollow-driven steel piles. Rammed posts combined with helical piles. Heavy hydraulic press machines were brought to the site, directly driving millions of galvanized steel piles through the sinking sand, planting them straight into the hard geological layer below. The spirals on the pile shafts create immense vertical friction, firmly anchoring the entire support frame to the ground. This mechanical structure helps the entire steel frame matrix stand firm and avoid being uprooted even when facing wind gusts over 150 kilometers per hour. Right after the pile foundation system was firmly set underground, the next step was activating a massive logistical campaign. Over 10 million photovoltaic modules were continuously transported by fleets of heavy trucks, forming long convoys across the desert terrain. At the construction site, engineers proceeded to bolt load-bearing aluminum rails onto the steel pile heads. Each solar panel was then placed on the support frame and securely locked using precise mechanical clamping systems. The entire surface of the panels was calculated to be installed at a fixed, tilted angle, ensuring they are perpendicular to the direction of solar radiation to harvest maximum light energy. As soon as the matrix of 10 million solar panels was fully assembled, engineers immediately had to face a severe environmental risk in the desert: sand dust. Continuous winds cover the glass surface with a thick layer. With just a thin layer of dust blocking the light, the power generation output of the entire system can drop by up to 30%. More dangerously in terms of physics, this dark shading activates the hotspot effect. The dust-covered battery cells cannot generate electricity. They turn into resistors, absorbing reverse current from other cells and self-heating their surfaces to extreme levels. which can cause permanent damage to the entire photovoltaic module. Normally, to clean large-scale solar power plants, people use high-pressure water tanker systems. However, in this dry desert region, finding millions of liters of industrial fresh water every day is impossible. To solve the surface cleaning problem, a completely dry cleaning robot system was deployed. Thousands of automated machines are mounted directly onto the sliding rails bordering the solar panels. To avoid the 50 degrees Celsius temperature during the day, this robot system is programmed to activate simultaneously at night when the glass surface has cooled down. Their operating mechanism relies on ultra-fine fiber rotating brush axes combined with a pressure air-blowing fan system. When moving across the thousands of kilometers long grid system, the robots scrape and blow all the sand and dust down to the ground completely without using a single drop of water, while ensuring no micro scratches are created on the glass surface. Once the problem of absorbing solar energy and maintaining efficiency was solved, the next step was to control and transmit this massive stream of energy. The photovoltaic modules on the desert surface only generate direct current, DC. This raw current must run through a matrix of thousands of industrial inverters to convert into alternating current, AC. However, to accurately manage a power system spread over 5,700 hectares, engineers cannot conduct manual monitoring. All operating parameters from these thousands of inverters are transmitted in parallel via a fiber optic network back to the project's Supervisory Control and Data Acquisition (SCADA) center. At this monitoring station, the operating team tracks voltage data in real time. The system allows them to instantly detect, locate, and isolate any malfunctioning module, ensuring the entire 2,245 megawatt machine is always in its most stable state. At the same time, in terms of physical transmission, the entire alternating current, after passing through the inverters, is routed directly to the ultra-high voltage substations located at the center of the project. At this switching yard, heavy-duty transformers raise the voltage level up to 765 kilovolts. Pushing the voltage to this maximum level follows a basic physical principle: to completely minimize energy loss in the form of heat, ensuring the current is transmitted intact over hundreds of kilometers through the high-voltage tower network to reach consumption centers. From a barren desert completely unlivable, the Bhadla Solar Park has become a giant power generation system with a capacity of 2,245 megawatts, providing clean energy to millions of households. This super infrastructure is the clearest proof of applying mechanics and engineering to conquer the harshest natural conditions. Thank you for watching. Don't forget to leave a comment below about the next infrastructure project you want us to analyze. See you in upcoming technical videos.